we're ready to look at confidence intervals, and we're going to start with the population mean. We can do confidence intervals of many different types of population parameters, but we're going to start with the population mean. And our goal here is to construct an interval using a sample mean that we're going to be able to conclude contains our population mean with some level of confidence. That's our goal here. So we're going to take a random sample from our population and calculate the sample mean, and we're going to construct an interval around that mean, and we're going to be able to deduce that the population mean lives inside that interval with some level of confidence. So we're going to say alpha is our significance level, which means 1 minus alpha times 100% is our confidence level, whatever that alpha is. Now I'm going to draw a picture here. We're going to use this to figure out why our interval is what it is. So if I take alpha and split it up into 2, so alpha over 2 is over here, and alpha over 2 is over there, that means 1 minus alpha is in the middle. It's yellow highlighted part. All right, so then this is z sub alpha over 2, and this is negative z sub alpha over 2. So what this picture illustrates, the yellow portion, the probability of being in that yellow portion is saying that you get a z value that's between negative z alpha over 2 and z alpha over 2, that probability is equivalent to 1 minus alpha. That's what this picture illustrates. Okay, so our process is we're going to take a sample, a random sample, and compute the sample mean. Okay, now the central limit theorem tells us that the sampling distribution of the mean is approximately normal, whose mean is the mean of the population, which we don't know, and whose variance is the variance of the population divided by the size of the sample. Okay, and in this first case here, we are going to assume, although we don't know the population mean, we assume we know sigma. Okay, so we know the population standard deviation. That's going to be case 1. So our central limit theorem tells us that that our sampling distribution of the mean is approximately normal. So we're going to convert that to our z-score, and we'll go back to this picture right here. So we had the probability that z was between z alpha, negative z sub alpha over 2, and z alpha over 2. That probability was equal to 1 minus alpha. That's from up here. And we're going to convert our x bar to a z our x bar to a z-score. So z is equal to x bar minus mu over sigma over the square root of n. This, by the way, is what we don't know. So we're going to place that right in here, replace our z, and then we are going to manipulate this algebraically until we get mu inside, just in between our inequalities. So we'll multiply all sides by sigma over the square root of n, and we end up with the probability negative z alpha over 2 times sigma over the square root of n is less than x bar minus mu less than z alpha over 2 times sigma over the square root of n. I'm just multiplying through by the common denominator. That is equal to 1 minus alpha. I'm going to subtract x bar from all sides. So I have minus x bar minus z alpha over 2 sigma over the square root of n less than minus mu less than z alpha over 2 sigma over the square root of n minus x bar. So I just subtracted x bar from all 3 sides, and I get 1 minus alpha there. Now, I'm going to multiply everything through by negative to get rid of that negative on my mu in the middle. which has the property that will flip the direction of the inequalities. So this becomes x bar plus z alpha over 2, sigma over the square root of n, greater than mu, greater than, these change to x bar minus z alpha over 2, sigma over the square root of n equals 1 minus alpha. And our last step is to write this in the order that we're used to reading inequalities, where the smallest is first. So we're just going to flip this around, and we get the probability x bar minus z alpha over 2, sigma over the square root of n, is less than mu, less than x bar plus z alpha over 2, sigma over the square root of n. And that's equal to 1 minus alpha. So let's see what this actually says. The probability, the population mean, is between this left endpoint and this right endpoint is 1 minus alpha, based on our central limit theorem. And that right there is our confidence interval. It's centered at the sample mean, and it's plus or minus z alpha over 2 times sigma over the square root of n. This piece right here, z alpha over 2 times sigma over the square root of n, is called the margin of error. Margin of error. And this sigma over the square root of n is called our standard error. So let's look at the process really quickly. We don't know the distribution of x, nor do we know the population mean, but we do know sigma. Okay, we take a sample of size n and calculate the sample mean. And then we find the margin of error, which is going to be z alpha over 2 times sigma that we know divided by the square root of n. So once we've done that, then we construct our interval by adding and subtracting it to both sides, and that is a confidence interval. This is a 1 minus alpha times 100% confidence interval of the population mean. In the next video, we'll look at what we do when we don't know sigma.